capturing all the data plane protocols. Okay? So BGP is the control plane for layer 3, but it's not in this figure. No. So think about that for a bit. It's a great point to make. This protocol diagram is capturing, if I have a data packet, if I go off on the internet and I catch a data packet, these are the set of protocols and headers I could expect to see. We actually don't have a nice layered equivalent for the control plane. Okay? We have control plane protocols that support the data plane at each of these layers, but not, we don't have an equivalent diagram. There is no control plane for the application layer, for example, or control plane for TCP. It's the IP header at some level, but also making the IP header worked meant you had to have forwarding tables, which then meant you needed link state and distance vector in BGP. You mean in a physical sense? Yeah, it bits on the wire, it's the header IP. So the question is, what do we mean by IP protocol? So strictly speaking, it's the IP protocol specification, it's the IP header. But then there's a lot of supporting infrastructure that has to go into making routers know how to treat that IP header. And there you get your routing, you get your management plane and all of that. Any other questions? Other things to note in this picture, you can have multiple versions in a particular layer. So for example, we had TCP and UDP. We also have things like Ethernet or the fiber protocol at the layer 2, but we only have one IP layer. Okay. So that is the principle, having this notion of layering and having one universal IP layer. Understand why it was important, not just the fact that we have it. And why was it important and useful was that innovation was able to proceed largely in parallel. Okay. This is the benefit of having that kind of modularity. Any other questions? I know it's been a while since we talked about layering and protocols and all of that. Okay, the last thing, one of these key design choices that you have to keep in mind was the end-to-end principle. And we've come back to the end-to-end principle repeatedly when we looked at decisions that were made while designing different protocols or different headers. Okay. The idea behind the end-to-end principle is it tells us what functionality gets implemented where in the network. And so remember, we said we had these 5 layers. In terms of what layers get implemented where, we said that all 5 layers get implemented at the end host, but only layer 1 to layer 3 gets implemented in the network. We talked about why at length. Did we do this split? Specifically, why did we not implement reliability in the network? And we attributed that decision to the end-to-end principle. We also several times have pointed out that the network layer gets implemented. It's the highest layer that gets implemented everywhere. The end-to-end principle was this argument from Dave Clark about how we reason about where to place functionality in a network. And we said the way we should think about it is, if you're thinking about implementing a function in the network, if you implement it in the network, is it completely and correctly implemented as a function? Or do you still need to implement it at the end host? And if you still need to implement it at the end host, can you get away with not implementing it in the network? Right? And something like reliability, we walked through this line of argument that said there is no scenario in which having reliable delivery in the network was going to be good enough to actually reliably transfer data between 2 applications. Right? Because worst case, your disk crashed at the receiver before you reliably transferred the data. And so if you're going to have to do this end-to-end check on whether your data was reliably transferred, then why bother doing it in the network? But we also said sometimes you might do it as an optimization, but not for correctness. Okay? That led us to this kind of layered breakdown. Okay, so we have layers, which is how you break things down. We have protocols, which is how you communicate between layers. And then we implement them through these headers and header encapsulation. So again, going back to the CEO example of you take a letter, you put it in an envelope, you put it again in a FedEx envelope. That's the role that headers are playing in this picture. Okay, so when you look at this picture, you should be comfortable with what headers are getting added where, what headers are being removed where, and you should be able to say, given a particular layer, what headers does that layer need to understand? Or when it receives a packet, what layer will be on that packet? Okay, and when it sends it up, which headers does it actually remove before sending it up, or which headers does it add before sending it down? So this entire process of header encapsulation and decapsulation, both what gets done, but also why it gets done. Okay. Any questions on this particular layering architecture? We then moved on to this kind of more complicated view of data packets flowing through the network. Like we said, we started at the application where we might have a protocol like HTTP. So we take some application data, we'll put it in an HTTP header, which is an application layer header. We would add a TCP header, add an IP header, add an Ethernet header, send it out. So when you walk through this, just test yourself, for example, by saying, okay, if I'm looking at this particular layer implementation here, the router, what headers does it have to understand? Okay. If I look at a packet over here on this link, what headers is it going to have? If I look at a packet as it's being transferred between the Ethernet to IP interface here, what headers does it have? Okay. Any questions on this one? No. Okay. So taking stock, we started looking at how we do things, and we were looking at the control plane, links, routers, topologies, domains, intra and inter-domain routing. Then we switched to why we do things a particular way. We talked best effort, layering, the end-to-end argument. There's one remaining topic, which is going back to the data plane, which is the design of IP. And I think our entire discussion of IP can be summarized by looking at this IP header. Okay, so you should know what all the fields here are in the sense of what role are they playing. So we had certain fields for parsing packets, certain fields for dealing with strange things that happen in the network, like loops or dead ends, not dead ends, loops or corruption. We have source and destination addresses and so on. Okay. So I think just looking at this, walking through each field, reminding yourself why it's there, why we needed it, what we do with that field, but also think about our discussion about which of these fields were working out well for the internet versus not, which ones were a good design decision versus not. And a lot of that discussion about why the header looks the way it does, or what we did or did not like about the header, you can remind yourself by just doing the comparison between IPv6 and IPv4. Like, why did we get rid of checksums? Why did we get rid of fragmentation? And so on. Yeah? Yes.
So I wonder if the checksum is not in the header, where is it?
Right. So where did the checksum go? Great question. If the end host wanted to check whether the packet was corrupted or not, we're going to have a checksum at a higher level in the TCP header when we get to it.
And another question, like at the same time, like what if something was corrupted in the header itself? Let's say, like maybe the address was corrupted, or like something important was corrupted that actually changed the nature of the header.
Right.
And can like give some malicious or like send a packet directly to some other host and like with some very like sensitive information.
Yeah, so what would have happened if, let's say the corruption, I think the worst you can think of is change some bits in the destination address. And so your packet was carried to a different destination. That destination, when it checks the checksum, it should fail.
But theoretically, if it had like my credit card information or something, then
Fair enough. Yeah, okay. What's the worst case you could construct?
or this is like so impossible that we don't like care about it.
Yes, and also because those checksums often get checked in practice on your network interface card. So, it's not even going to make it to a malicious. You'd have to have a a lucky recipient that received it by having some bits twiddled, unfortunately on the wire. So, and a totally innocent destination just lucked out and got that packet and actually knew how to go into your operating system and fish that packet out before it got dropped and said, let me check if there's... So you'd have to have malicious code sitting on a lucky host able to tap into your operating system. So I think in practice, people don't worry. Any other questions on... Any other questions on any of the material? Go ahead.
So when we did the relations, we said we were going to send path vectors to avoid loops. And there just seems like such an elegant solution to avoid loops. And previously we did some in my opinion, ad hoc solutions, which is voice in reverse and like those just seem much less elegant than just doing path vector. Why didn't we do path vector for it?
Yeah. So the question is, why didn't we do path vector for intra-domain routing? I think it's largely historical. Probably at the time people were also worried about long paths, and so then if within a domain you were advertising very long paths, this would have been a problem. I suspect if you looked now at this point in time, if we got to wipe the slate clean and redo intra-domain routing, we would say, okay, 100 hops, even that is not that many bytes. But if you go back to the time when people were designing these, they were very low bandwidth links. Right? We're talking about 10 kilobit per second links. So this idea of sending large exchanges across a network topology that we don't know about was concerning. So for scalability reasons. That is the other thing about the internet is, it's an evolving thing. You don't get to just reinvent it tomorrow. Any other questions? Okay, with that then, I think that's all I had. All the best. Good luck on the exam. I don't think it's a particularly difficult one. But...